So to work with equilibrium, we calculate the equilibrium constant using the equilibrium expression. Now, the equilibrium expression is this here. So what we do is we grab the products and we divide it by the reactants down here. And we grab each of the individual concentration and raise it to the power of its stoichiometric ratio. And that gives us a number that stays the same. So if these numbers change, and they reach equilibrium, then the equilibrium constant will still be the same. And so we're using this square bracket symbol to represent concentration because it's neater and quicker. And we haven't gone into the changes yet, but the only thing where Kc changes is temperature. And so when we use catalyst concentration or pressure, which we'll explain later, Kc always remains the same if it's at equilibrium. So one thing to note with the Kc, because solids and liquids have relatively constant concentrations and usually quite large values, they'll obscure the Kc value and make it difficult to use. And so we delete them from heterogeneous equations. So just double check that your equation is heterogeneous or homogeneous. If it's heterogeneous, get rid of solids or liquids, and then you can go ahead and write your expression. So products to the power of 2 divided by reactants, which is to the power of 1. So that's the correct Kc expression to get the correct equilibrium constant. Same with this one here. Some is in aqueous, some is in liquid. That's relatively constant and very large. Get rid of that. And so we rewrite this, they're all to the power of 1. Okay, so that's the Kc or K value for this particular equation. Sort of jumping ahead, that's actually Ka for high levels later on with acids and bases. Okay, now just to be aware that the magic number is 1,000 or sig fig of sort of three decimal places or to the power of 3. If it's greater or less than that, it's considered significant or not. In this case, we're talking about whether it's going to go to completion or not completion. So just have a look at these values. If everything's 1, that means pretty much there's 50-50 on either side. Now, if it's less than 1 here, so it's reactants go to products, and the Kc is products over reactants. So that's how you work it out, by the way. So if the Kc is greater than 1, I should say, then it's favoring the products. If it's less than 1, then the reactants are greater, and then it's favoring the reactants. Now, if it's 10 to the positive 3 or 10 to the minus 3, we consider most of it going either to the products over here or most of it being on the reactant side. And that's important for your understanding for many reactions coming up. And one small thing, a mathematical trick. If you inverse these and put one side on the other, make sure you don't forget to inverse these things here or do K to the minus 1 because of this mathematical rule here. So just going to a practice question. This is a typical question. You'll have to write the Kc expression and then sub the values in to get the equilibrium constant. So there we've got the products here on the top to the power of 2 and the reactants on the bottom, don't forget, to the power of 2. Simply sub those numbers in, get that number, and then determine what we're going here. So this number is very, very large, and so the majority of it will end up going to products.